So today we are going to talk about pre-calc concept called Gaussian elimination, named after a mathematician, Carl Gauss. So he kind of took elimination and made it work for variables besides just x and y. So what happens if I have x, y, and z, or w, x, y, and z, or maybe u, v, w, x, y, z, or different variables. Of course, it doesn't have to just be the end of the alphabet, but he kind of created a process to use elimination for multiple variables. So if there's multiple variables, that means there's going to be multiple equations. Generally, the number of variables in your equation or in your system kind of portray or give you an idea of the number of equations that you should have. So if I have 3 variables, I should have 3 equations. If I have 4 variables, we should have 4 equations. So we're going to start looking at that today, talking also about this row echelon form, which is a form that we will get our equations, our system of equations in order to solve for those variables. So we will work with that today, tomorrow, and Thursday, Jack.
Is that the same, is that also related to like Gaussian order? It's like an effect that is spelled the same as Gaussian order.
Oh, maybe. I'll have to look. So what is it called?
It's spelled the same as Gaussian.
As Gaussian elimination. Could be.
The type of blur that's like just general blur.
Huh.
As opposed to like directional.
Maybe. I will need to look it up. I will look. You can look too, Jack. See what you can find. So your homework tonight, notice there's 5 problems. And I think tomorrow there are 5 or 6 problems, because the problems are a little bigger, a little more involved than just your basic set of 2 equations. So definitely a little more involved. So 5 questions tonight. And we will go through a few examples today so that you kind of get the feeling of how this Gaussian elimination works. We'll cover tomorrow Gaussian elimination again, but we're going to look at systems that are non-square and some applications tomorrow. And then Thursday, I have built in as a review day of this Gaussian elimination. And then we will start partial fractions. So Gaussian elimination kind of feeds into these partial fractions, decomposing fractions, breaking them down. Does anybody have a compost at the back of their yard, compost bin? Yes, good. So we're decomposing fractions instead of compost. Did you find it?
Yeah, it says in image processing, a Gaussian blur, also known as Gaussian smoothing, is the result of blurring an image by a Gaussian function named after mathematician and scientist Carl Gauss.
Ah, there you go. So it is. Oh, I'll have to look into that a little more, Jack. Thanks. Good job for recognizing that. So quickly, I'm going to go over number 10 from the homework. That was a special type of factor by grouping. So I just want to go over that. I should have it on the bottom of my screen and I don't, but there will be a factoring quiz on Thursday. So Thursday is our like little review summary day of this Gaussian elimination. And there will be an 8-question factoring quiz on Thursday. Saying that the quizzes that you took on Wednesday prior to break, remember you took a little quiz then, those scores I literally just entered into PowerSchool last period. So PowerSchool is updated. I believe the quizzes should have been sent back to you so that you can look at that information. If you submitted a test buyback, I did not. Literally after I got to my parents' house on Wednesday at 8 o'clock, I kind of shut off Google Classrooms. I did not look at any of that, but I will get that information back to you if you submitted the test corrections for the and the practice worksheet for the buyback. So I will look at that today. It's on my list of things to do. Right. Let's look at number 10 from the factoring worksheet a little bit here because it was a special factoring problem. Then we'll get into this Gaussian elimination. So number 10 is a grouping problem. Pretty much if there are 4 terms, you're going to use factor by grouping. This is a special case of factor by grouping. You are still going to group the first pair together and the second pair. So factor by grouping, generally you group pairs together if you have 4 terms. At usually 95% of the problems, you group a pair together. If you group 4x squared minus y squared together, there is no GCF to pull out. They don't have an x in common. They don't have a y in common. They don't have a number in common. But there's still a way to factor that. Cole, how would you factor 4x squared minus y squared? Yeah. So it is still a type of factoring. Not always do you have to just pull a GCF out. You're still grouping, but instead of pulling a GCF, you're factoring because they're a perfect square. Now, the second group, 2x minus y. Again, they don't have anything in common. It's just 2x minus y. However, for you to do truly factor by grouping, you are supposed to be able to group something from one and something from another together. So you split the line down the middle, and then you're supposed to group things together to completely factor it. Well, I'm going to pull out a 1 from that just so that I'm pulling something out because there really is no way to factor that. And then we have 2x minus y. So factor by grouping works because there is a quantity in parentheses that is the same. Because that quantity is the same, you have like terms because this is not complete multiplication. This is still a sum problem. There's still an addition sign here. If you look, the quantity 2x minus y and 2x minus y is that quantity that's the same. That must occur for you to be able to group the other two quantities together. And those quantities that you would group together would be the 2x plus y and the plus 1. Because they're both like terms, they're both being multiplied by the same parenthesis. So factor by grouping, you group the parenthesis that's the same together. So I'm going to pull that 2x minus y. That's the quantity that's the same. And then you group anything else that was being multiplied by that same quantity together as well. And that would be the 2x plus y from the first pair and then the plus 1 from the second pair. So if you were looking at the answer key and you were thinking, how the heck did she get a plus 1? That plus 1 is from that second pair of terms that you grouped together because they still have something in common, even though it's a number 1. And for factor by grouping to work, you must pull something from the second pair and something from the first pair together because they're being multiplied by the same factor in parentheses. Questions with that? You'll see that that's like special case of factor by grouping. And that's something that you only see probably, I don't know, 1 out of 70, 80 problems. It's not very often that you see that type of factoring. All right, so we are going to start using this Gaussian elimination. The factoring we will kind of pull in once we start talking about partial fractions. So we will be using factoring as a way to help us with these partial fractions. Gaussian elimination will also help us with partial fractions. So little warm-up problem here. It says solve the system, check your solution. Notice that we have 3 systems, 3 equations, not systems. The first equation has 3 variables, the second has 2, and the last one just has z. See if you can solve the system. So if there's an x, y, and z, you need an x, y, and z. It's called an ordered triple instead of an ordered pair. Think about how would you solve this system? Evan, how would you solve the system? What do you think you would do? No, I got no clue. What's the third equation that they give you? Yeah, so substitute, they give you z equals 2. So let's substitute that in to the previous equation that has just a y and a z. So y plus 3, z is 2. So we're actually solving using substitution because they give you the third variable, so you can substitute it in. And you know y is, yeah, positive or negative?
Or negative.
Negative. Okay, so now we have y being -1 and z being 2. Grant, what would you do next? Yeah, plug it into the top equation because the top equation not only has a y and a z, but it has x, which we're trying to solve for. So x minus 2 times -1, 3 times z, 1z is 2, it's always 2, and that's equal to 9. So this becomes x plus 2 plus 6 equals 9. So Grant, x is equal to 1. How do you write your answer? How do you think you'd write this solution, Peter? It does not have to be that. No. Anna? So how would you? 1, -1, and then 2. So think about when you had 2 variables, when you're solving a system. So I have x plus y equals 1, 2x minus y equals -1. What are you really finding when you solve a system with 2 variables? A point. So I have one line, if I have a line, and another line, and you're finding the point where they cross. Well, now I actually have 3 lines. They're all linear, and I don't have another arm. So obviously I can't make my third arm cross, but we're still finding the point where these 3 lines intersect. That third variable creates a third dimension. Calc 3 is multi-dimension calculus, so you'll deal with things in 3 dimensions in Calc 3 if you get there at some point, depending on obviously the course that you take. But this is an ordered triple representing the point where all 3 of these lines intersect. That the third line kind of goes through a third dimension, so it kind of comes out at you by my x, y, and then that third dimension, the z, creates a 3-dimensional equation, a 3-dimensional graph. It does say to check your solution, which you can always do when you're solving for any variable. If you plug them in, we have a 1, a -1, and a 2. So this definitely, oops, there's my 2. That works. And then if I plug in -1, 3 times 2, that also works. And of course, then z is 2. I'm not going to plug that in. If it doesn't work for one equation, it's not a solution and you did something wrong, probably. So it must work for all 3 for it to be a solution. So this is my little check step over here. So in the little blurb below, it says the above system is in row echelon form. So row echelon form, we kind of say has a stair step pattern. So you kind of think you're going up the stairs or down the stairs. Each time you move down an equation, you have one less variable. So this form is going to be the goal of Gaussian elimination. So can I take an equation that has 3 variables, a second and a third equation that also has 3 variables, and can we get it to look like row echelon form? Row echelon form, I can then use back substitution. That's what we used. So essentially you took the third variable, you went backwards into the previous problem and plugged it in. You took those 2 variables, you went backwards and plugged it into the first equation, and you solved. So the form is row echelon form. The process is called back substitution. To get there, we're going to use Gaussian elimination. all these terms that we're looking at. So if you look, our next system here is not in row echelon form. So I don't have a stair step pattern where the first equation has all three, and then the second one has two. It does have two, but it doesn't have that first variable missing. And then the third equation has three. Gaussian elimination is a process to get a system of equations in row echelon form. There are many ways to do this. In math, you at this point know that there's not just one way to solve a problem, especially in trig. You saw there wasn't one way to solve an identity. So it says the book suggests leaving the x in the upper left-hand corner and eliminate the other x's in the first column. So what we're going to try and do is we're going to try and leave this first equation be. We're going to keep that equation there. Our goal is going to get it to look like row echelon form. We want to eliminate the x's underneath it so that they disappear. So we're going to use a form of elimination, and that elimination is named by Carl Friedrich Gauss, so a mathematician that was born in the 1800s, or that lived, I should say, in the 1800s. So if you look, we're going to start pairing equations together, and we're going to start by pairing the first two equations together. If you pair these two equations together and use elimination, so I'm going to write them over here on the side here. So my first equation stays the same. I'm going to look at the second equation. If you just add these two equations together, what would happen with them, Peter? The x's will cancel. So we're going to add these two equations to get the x's to cancel. Because again, the goal is to try and get this to look like a stair step problem. I want to eliminate the x's underneath. So Peter, if you add the two equations together, what do you get? Yeah. Now I know you're saying, but hey, we didn't have a z variable and now you threw a z variable in. That's okay. The whole goal is to get it to look like the above problem. We don't want an x. I want this 3 variable, 2 variable, 1 variable form. This equation that we found, that Peter gave us, is called a resulting equation. It is going to replace the first equation that we had. So I still have the x minus 2y plus 3z equals 9. But once I added the first two equations together, the resulting equation replaces that middle equation. So my middle equation is now y plus 3z equals 5. Notice now it kind of looks like a stair. I have one equation, the first one with 3 variables, and the second equation no longer has an x. It's gone. So I have kind of the row echelon form starting to happen, Peter. Because the top equation, I still need it. It can't disappear. And that is kind of like our foundation equation. That's the equation that contains the 3 variables so that I still have all 3 variables in the problem because I have to have all 3 variables. So it's the second one that we're trying to eliminate the x underneath it. All right, so what we're going to do is we're going to go back and we're going to have to do this a second time. Our goal is to get rid of this x. So the goal is to have no x's underneath. So here's my x. I don't want to have any x's underneath that x. The first equation stays there. It stays the same. We now need to get rid of that 2x that's in the third equation. So if you look at equation number 1, think of that as like your base equation. What could you multiply equation number 1 by to get rid of the 2x in equation 3? So think of this as like equation 1 equation 2, equation 3. I mean, there are 3 equations. So Cole, what can we multiply equation 1 by to eliminate the 2x in equation 3? Yeah, so we're going to take that whole equation. We're going to multiply this by 2. And I'm going to say, let's just multiply it by -2 so we can just add those together. So our equation number 1, we're multiplying it by -2. That's the elimination part. So -2x plus 4y minus 6z is equal to -18. Our second equation, we're not worried about, but the third equation says positive 2x minus 5y plus 5z equals 17. And Cole, when you add those 2 equations together, what do you end up having?
Y minus Z.
Yeah, this is my fault here. Equals -1. So again, this is my second resulting equation. I'm going to take that result and I'm going to place it underneath. So my third equation is gone. I now have its result -y minus z equals -1. This is now starting to look like row echelon form. My first equation has the initial 3 variables. We use the first equation to eliminate the x's underneath. So now we have the first equation with 3 variables, and then the pair underneath have the same variables. They both have a y and they both have a z. Our goal is to get the equation to be in total row echelon form, so that I have 3, 2, and then my final variable, I'm going to get z to be totally by itself. So if you look at the 2 resulting equations, what can you do with those resulting equations to try and get z by itself? Parker, what do you think? Yeah, we can add them. So we can take the resulting equation, y plus 3z equals 5. -y minus z equals -1. Those are my results. And add them together. And when you do that, Parker, what do you end up with? Yeah, you're right. So we end up with 2z equals 4 or z equals 2. So in my form, my final equation was -y minus z equals -1. Well, this equation now, we can replace with z equals 2. And then I have the stair step form. So we used elimination 3 times. There were 3 equations and 3 variables. So the number of variables kind of depicts the number of times that you will have to use elimination. So if you look at the equations, we have x minus 2y plus 3z equals 9, y plus 3z equals 5, and now we have z equaling 2 because we found the third variable. If you go back to the first equation, the first system, notice that is exactly what I gave you to start with. So we took a system that was not in Gaussian or row echelon form. We used elimination, Gaussian elimination 3 times, and we now have it in row echelon form. So then I can use substitution and find the ordered triple. Now, because it's the same as the previous problem, we're not going to go through and solve it because it's the same exact as the previous problem. But you can see why I only gave you 5 problems, because you get to use elimination 3 times, and then you're going to have to use substitution twice. And finally, write your system as an ordered triple. So we're going to try this again and see if we can work through it another time. And we're going to try and keep the process the same. So if you keep the process the same and get used to the process, it does become a little less foreign. So again, think of this as equation 1, 2, and 3. Equation 1 always stays the same. Think of that as like your parent equation. It's not going to change. We want to change the equations underneath. So our goal is to eliminate the x's underneath by keeping that first equation the same, but also by using that first equation to help us eliminate the x's. Evan, what's going on over there? It's like making some kind of water sound. Not leaking, right? You don't see water coming out. No. Okay. Not really sure what it's doing. So I'm going to write the first equation again so that I know that I'm keeping that equation the same. Kaden, what would we multiply equation 1 by so that we can eliminate x in equation 2? Yeah, so let's multiply this by -2. So that becomes -2x, positive 6y, minus 2z equals -2. And then we are keeping 2x minus y minus 2z equals 2. And Kaden, if we add those two equations together, what is your resulting equation? So I'm going to write that underneath my first original equation. So we're taking out equation 2 and rewriting it with my resulting equation. All right, so we're going to go back to the original problem. And now we're going to pair 1 and 3 together. Joe, how can you take 1 and eliminate an x from the third equation? Yeah, you can just subtract them. So we're just going to subtract that whole third equation. Joe, when you do that, what do you get? So my third equation, -5y plus 4z equals 2. So we used elimination twice. We eliminated the 2 x's in equation 2 and equation 3. And now this looks very similar to having row echelon form. But the goal is to get the third equation to say z. Z equals something. Z equals 2, z equals 5, z equals 7, whatever it happens to be. So Gianna, what do you think you would try next? Yeah. So we're going to take those pair of equations. Those are our 2 results. And we're going to use them. And Gianna, when you add them together, what do you get? Careful. So we have 5y minus 4z is 0. -5y plus 4z equals 2. So if I add them together, yeah, you get 0 equals 2. What does that mean? Peter? Oh, sorry, Gianna, go for it. Nope, you're good. There is no solution. So that means that I now have these 3 lines. Remember the third being in a third dimension. They're not connecting. They're not intersecting. There is no intersection point for my problem. Questions? All right, so we're gonna try this one more time in example 3. What do you notice about example 3? Anna? Yeah, the second one doesn't have an X. So you're like, yay, one less step. Again, 3 variables. You have to use elimination 3 times. But if the second equation has no X, then you don't need to use elimination to get rid of it because it isn't there. So we're going to look at equation 1, keep equation 2 the same, and let's worry about getting that X out of equation 3. Jenny, how could we get that X out of equation 3? Yeah. So it is already negative. You can just use good old elimination to get it to cancel. And what do you get, Jenny? Good. Please make sure that you don't forget that Z is still there. You're not adding anything to it, but it's still in the problem. So we have these 2 equations. And now our third equation becomes 3y minus 3z equals 0. So the first goal when you're solving this problem, you want to eliminate both x's so that the pair of equations that you have underneath that first equation has just an y and a z. So what do you think you would do next? Peter? Yeah, so he said multiply that second equation because now you're looking at those 2 results. We're going to multiply that by 3 or -3, whichever you prefer, because we're going to try and eliminate the y. So after you eliminate x, the next variable to eliminate is y, so that you have an equation that says z equals. Peter, when you do that, what do you end up with? I don't think you did it wrong. I just multiplied by a -3 instead of a +3. I don't think you did it wrong though. Because you have to subtract your equations. So you end up with 0 equals 0, which means there are infinite solutions. Now, when there were infinite solutions and you had 2 equations, those infinite solutions pertain to a particular line. So there were infinite solutions, but those infinite solutions must be on the line that those 2 equations created. With an ordered triple, there are still infinite solutions. However, those solutions must meet a specific pattern. So I can't just pick 3 random numbers out of the air because I like those 3 numbers. Those numbers have to meet a specific pattern. And here's where the problem gets a little weird. So you cannot just say there are infinite solutions and be done with the problem. We have to still write a triple, an ordered triple, which is in the form x, y, and z. That's how my solution should look. I should have 3 numbers that represent the solution. But those 3 numbers must meet a special pattern in order to get these 3 equations to intersect. So the way you find that special pattern is to take one of your equations that contain both y and z. And we're going to try and use that equation to help us create a pattern. Now, z is the third variable that we usually solve for. So we always say z equals 2 in the first equation. We have z so that we can use back substitution to find the others. So we're going to take that variable z and we're going to let it equal an arbitrary variable. So we just want to let it equal an arbitrary number. And we're going to just let it equal a. I'm not going to use z because z is the variable you're solving for. A represents any number. So a is equal to any number. It makes sense to use a. So you're saying, all right, I'm going to base my solution on z because it's usually the variable you solve for. And we're going to say, let z be any number. So z is allowed to be anything. But the other two variables are going to have to match specifically to the equations that you're given. So we're going to take that variable z, and you're going to go into one of the equations that contain y and z. And let's just use the y minus z equals 0. In that equation, y minus z equals 0, you're going to replace z with a. So now I'm trying to find a way to write the solution to match the equations that were given. If you solve for y, you find that y is also equal to a. What does that mean about y and z? They're the same. So they're both ones, they're both twos, they're both fives, they're both 100s. They're going to be exactly the same. So now we're going to take my y variable and the z variable and go back into the first equation and figure out a way to write or represent x. So the first equation says x plus y. Well, y is now a. Minus 3z, well, z is also a because y and z are the same, equals -1. We're going to solve for x to have a representation for x. So this is x minus 2a equals -1. So if I solve for x, I get 2a minus 1. So that means x must be 2 times a and then -1. So my x variable now has a way to represent it as well. So our ordered triple is going to be 2a minus 1, that's x, and then y, and then z. So if I say, let's make z be 1. If z is 1, y is 1, what must x be? 1. Now I have a solution. But I could also say, let's let z equals 2. And then my y is 2, my z is 2. But the a value would be 3. So I can still find an infinite number of solutions, but those infinite number of solutions must meet that pattern. So they can't just be a random number or ordered triple. Questions. So when you get infinite solutions, you can't stop. You're going to always start with the z variable because that's generally the third variable that we try and get by itself. And you can just say let it equal a. And then we're still using back substitution to find the previous values, but we're not substituting a number. 5 questions for homework. Make sure you show all of your work. Check those answers in the back of the book. Have a fantastic day.
Have a good day, Ms.